Hi everyone, welcome to lesson 7 of the Advanced Higher Stats course. This video covers the Poisson distribution and is one of many videos that will be doing so. You will find this skill on page 21 of the 2023 course spec. By the end of this lesson, you should understand the criteria X must meet to follow a Poisson distribution. You should know how to calculate the parameters of a Poisson distribution, how to calculate exact Poisson probabilities using a formula, and how to calculate Poisson probabilities using your data booklet. Jumping straight into it, the conditions you need to use a Poisson distribution are the trials being independent, the number of trials being large, and the average rate of an event occurring per time period is constant. So, for example, the average number of rainy days in a week is 2 and is consistently 2, no matter if it's summer or winter. Here we can look at the similarities and differences for assumptions needed for the Poisson and binomial distribution. So some similarities are independent variables. You need them for Poisson and for binomial. Another similarity is the average rate of an event occurring per time period is constant. And that's the same as saying P is the same and Q is the same. So the probability of success is the same and the probability of failure is the same throughout every trial. The differing point here, though, is the number of events. So the number of events or the number of trials for Poisson is large, and we assume it's large, whereas the number of trials for binomials is fixed. Let's do the following question. We will need the data booklet for this, and we will need to look at page 4. In a shared university flat, the average number of times a student gets locked out of the room every week is 2. Get an assumption, then write the parameters and variance for this Poisson distribution. One assumption we have here is that the students getting locked out is random. So we ignore that the first week, maybe the students go to a lot of lectures and they leave the room a lot, and maybe at the end of the final weeks of the semester, they just kind of stay in and watch recorded ones, and they might have a less likelihood of leaving their room and getting locked out. Or if some parties are on some weeks and aren't on others, we ignore that. So that is independent. Write the parameters and variance for this Poisson distribution. So if we look at page 4 of our data booklet, we will see that the mean for the Poisson is lambda, and variance is also lambda. So what's lambda? That's just the average rate of the event, which is 2. So lambda equals 2. So how we would write this, the parameters is Poisson is 2. And that accounts for both the mean and the variance. Very simple. Now, calculate the probability of exactly 0, 1, 2, 3, and 4 students being locked out of the flat per week. Show this in a table. Well, let's use the formula. It's a pretty scary formula, but we got calculators. It's fine. So we have the value of x first, which is 0, 1, 2, 3, and 4. And then we have the probability of it actually being 1, 2, 3, 4, 0. And we just input the numbers here. And x is the number we're looking for, so 0, 1, 2, 3, 4. And lambda is what we just calculated, the average rate of an event. So I'll let you do this, and I will just skip straight to a fill table. Okay, so the values we have is for 0, it should be 0.1353. For 1, it should be 0.2707. For 2, it should be 0.2707 as well. For 3, 0.1804. And for 4, it's 0.0902. Remember to write to 4 decimal places. Here we have the Poisson distribution visualized in the form of a graph. So it's the same question, lambda is still 2. And one thing you would have noticed in the previous slide was the probability of x being 1 or being lambda is the same. And that's just something unique about the Poisson distribution. I can't really explain why. You'll also notice that unlike the binomial distribution, it is not symmetrical. The probability of x being 3 is lower than 1, and the probability of x being 4 is lower than 0. Now let's try the following questions. Edinburgh on average experiences a sunny day once every 4 days. State an assumption, then write the parameters and variance for the Poisson distribution. An assumption here could be that the sunny days are independent from the season. So you will get the same number of sunny days in June as you would in December. Lambda for this question would be 1. So you would write Poisson is 1 and v of x is 1. Find the probability of exactly 2 sunny days in 4 days. Here we use the formula. So we would write probability of x equal to is equal to e to the negative 1 times 1 squared over 2 factorial. And that should give us 0.1839. Next is find the probability of exactly 11 sunny days in 28 days. Now here we have to add one extra step. So we know for one sunny day every 4 days, lambda is 1. So 28 days, the number of days has been increased by a factor of 7. So 7 times 4 is 28. So we also times lambda by 7. So for this question, lambda is 7 because 7 times 1 is 7. And everything else is the exact same. We use the same formula. Probability of x equaling 11 is equal to e to the negative 7, because it's 7 now, not 1, times 7 to the power of 11 over 11 factorial. And that gives us 0.0452. 0.0452. Now let's try some trickier questions. It's the same question. Lambda is 1. Find the probability of the number of sunny days not being 4 out of 4 days. Here, we have to first find the probability of the sunny days being 4 out of 4 days, which is e negative 1 times 1 to the power of 4 over 4 factorial. And that gives us 0.0153. And how we find the probability of x not being 4 is equal to 1 minus the probability of x being 4, which is 1 minus 0.0153, and that should give us 0.9847. Next question. What is the probability that a Poisson variable with mean 5 will produce exactly 2 3s in 4 trials? So this is unrelated to the Edinburgh question. And we are given lambda, which is 5, exactly 2 3s in 4 trials. So we need to know the probability of x being 3 and x not being 3. We can do that with the formulas. I will skip writing the whole formulas down, but the answers you should get are 0.1404 for x being 3 and 0.8596 for it not being 3. So we have 4 trials. So we want 2 of them to be x being 3. And then we want 2 of them to be x not being 3. So that would give us 0.0146. A tree diagram might make you understand this a bit better. It's basically it basically just is a tree diagram. So the likelihood of x being 3 and x not being 3, and then you just keep on going and you calculate that. So that's basically what I'm doing with these events here. Your data booklet also has a Poisson distribution table. You will find that on page 10. And just like the binomial one, the probabilities you'll be given will equal to the probability of x being less than or equal to a number. So if we have to use that, just on the same question where there was one sunny day in Edinburgh out of every 4 days, so lambda is 1. If we want to find the probability of there being at most 2 sunny days out of the 4 days, we go along the table. So lambda is 1. Then we go down to our x value that we want. And then this intersection here will give us our probability. So that means the probability of x being less than or equal to 2, or the number of sunny days being 2 or less, is 0.9197. Try the following questions yourself. The average number of coughs in one lecture is 10. Find the probability of it being at most 8. So, probability of x being less than or equal to 8 is what we're trying to find. Our lambda is 10. 10 coughs per lecture is the average number. So we just go along the table. 10 is all the way here, and we want to find x is equal to 8. So that is this number here. So that's 0.3328. Okay. And the probability of it being less than 4. The probability of x being less than 4. We have to be careful here. This is less than 4, not less than or equal to. So what this equals to, or we can find instead, and it's the same value, as the probability of x being less than or equal to 3. And we can find that value in the table. And again, the same thing. We go on to the lambda equals 10. We look for x being 3, and we get 0.0103. Okay, find the probability of it being at least 14. The probability of x being greater than or equal to 14. So to find this, it's the same as 1 minus the probability of x being equal to or less than 13. And that is 1 minus, and we use our table again. Lambda is 10, we go down to 13, we get 0.8645. And then the answer we should get is 0.1355. All right, this final and trickier question. The average number of coughs in one lecture is 10, lambda is 10. Find the probability of the number of coughs being greater than 5, but a maximum of 18. Okay, this one is a bit tricky. What we have to do here, let's find the probability of x being a maximum of 18 first. And that is simple. We look at lambda 8, lambda 10, go down to 18, and we get 0.9928. So this is the number of cuffs being at most 18 and ranging all the way down to 0. But we want to find the number of cuffs between 5 and 18, so being greater than 5. That means we have to find the probability of x being 5 or less. Using the table. That is 0.0671. And now we just find a difference between these two values and we'll get the value for our answer. So the probability of 5 being less than x, but x being less than or equal to 18 is equal to the probability of x being equal to or less than 18 minus the probability of x being less than or equal to 5, which is 0.9928 minus 0.0671, and that should give us 0.9257. That's the end of the first Poisson distribution lesson. So now you should be able to understand the criteria X must meet to follow a Poisson distribution, how to calculate the parameters of a Poisson distribution, how to calculate the exact Poisson probabilities using a formula, and how to calculate Poisson probabilities using your data booklet.